right, welcome to this walkthrough of another prediction pipeline. We've got a different task this time. We're going to be predicting a category instead of predicting a numerical value. The category is going to be a long length of stay. Can we predict patients that will have a long length of stay? A common type of question that would come up in healthcare. We're going to define long length of stay as greater than 4 days. And so we start by getting all of the libraries we need in order to manipulate data and do some plotting, as well as the scikit-learn libraries that we're going to need for all of the different prediction tasks later in the code. Then we have to connect to BigQuery and get this established. What is the data set we're pointing to when we query, so that we can build a query like this and return data about our patients. And so you can see here we're gathering some of that basic hospital encounter information with their length of stay and some other describing information. And then we want to just start looking at it visually. Let's get the distribution out and see what length of stay looks like. That is pretty common to witness. And then a classification of that long stay patient. 0 if it's not a long stay, 1 if it is. Remember, our definition is going to be greater than 4 days. Okay, next we want to check when we split into training and testing, like we're doing here, what's the prevalence of those long stays? It looks like it's just about the same between the both of them, around 60%. So this is just a quick test to say, all right, we split it, but did we accidentally get too many of the example in our training or our testing? And that doesn't seem to be the case. Next, I just want to talk about a concept of leakage. The idea that you could accidentally get data from the whole data set into your training so that it can learn something and do better at the prediction task. This is going to overstate the capability of the modeling approach. So one of the ways this can just sort of accidentally happen is when we scale our numerical columns or we normalize them. So instead of having them a length of stay between 1 day and 60 days, it can help to take all those numerical columns and shrink them to some range between 0 and 1. To do that, it has to learn the distribution of the data. And what can accidentally happen often if people aren't very thoughtful is they can build that scaler that does the normalization of the data based on all the data versus just what we're training on. So this is just a quick little warning section to show you, hey, guess what? If you did that by accident, you're going to be giving the answers to the test to your prediction model. Because there really is a difference between what we picked out for training and what the overall data has. And the overall data, if you give it that scaling information, you're accidentally leaking a bit of the answers to the test in a subtle way, but you are. So it's just something to make sure to think about, and I just wanted to show you that example because it might be something you hadn't heard of. Next, we're going to get a pipeline just sort of established, and I'll visualize it here for you. For our numerical columns, we're going to do a simple imputer. It looks like we just have age there, and we're going to do a median there for the age whenever it is blank, if it is blank, and then we will use our scaler. On our categorical variables, which are going to be, we'll use a I'll expand this so we can see. The categorical variables are sex and the DRG. And for our simple imputer, we're going to use a strategy of most frequent. If it is blank, we'll use the most frequent value. Then we will one-hot encode those, and then we're going to send it into a linear regression. So that's the pipeline that we're about to operate with. Looks a bit like that, and this is a nice way to get it out so it's just visual and you have an ability to sort of observe that. I like this little step. You can keep it if you like it. All right, we want to do a cross-validation and go ahead and do this training across many different folds of the data and make sure that we are going to have a good opportunity to observe a realistic type of performance with holdout data and then validating across a couple different folds and and versions of that. And so we see here that we get a ROC AUC accuracy based on recall 0.86 plus minus 0.025. So not a huge plus minus. That's good to see. And then our precision, we're going to talk about precision and recall more later, of 0.91 plus minus 0.02. So that's what comes out when we do a cross-validation, which is generally showing pretty good results. And so now we're ready to do a little more formal evaluation of, all right, how well is this doing, and does this matter? That's the last step not enough people take. You can find 1,000 courses online about how to test the accuracy of your predictive model. So if I don't hit it deep enough, you can go and find tons and tons of content. What is rarely discussed is how do you translate that into something useful for like your administrative colleagues, your clinical colleagues, so that you can discuss the actual real life trade-offs of using a predictive model. So we're going to start with the core concepts, and in a categorical prediction task, the core concepts are going to be something like this confusion matrix. What can happen when you predict a category of something happening, yes, this will happen, is you can be right. You can have true positives where we said they will be a long stay, and they were. You can be wrong. You can say they were going to stay long, and they can miss the mark. Or we missed the mark. They did not stay long. We also are going to we're going to say for some of the patients, no, we don't think they're a long stay, but they will end up being a long stay. We want to know how often that happens versus when we say they won't be a long stay, but they end up being a long stay. So those are the different parts of this confusion matrix. All four of those things are possible. And I'll just quickly zoom down to the answer. What does that look like in our data? Here's how many times we said there would be long stay, and they were. Here's how many times we said they would be long stay, but they weren't actually. And if we said they wouldn't, this is how often that was true. And there are if we said that they would not be long stay, here is how often we were wrong. And then this is the times we were right. We said, no, they're not going to be long stay, and they weren't. This is 72. So that's kind of the answer in this data set. Generally quite a good performance. This also is based on a threshold of probability. We have to decide which bucket to put them in depending on the probability that we see in our model. So that's something we can change, and we'll evaluate later on in the code. So that's jumping to the answer, but let's explain it a little bit more. There's two things that we're going to look at to understand how this model is performing. One of them is going to be recall. And so recall, also talked about as sensitivity or the positive rate, is how often we were right when we said someone would be a long stay, divided by how many times we were right of all the actual long stay patients. Which fraction did we catch? So if there were 100 patients that stayed long, did we catch 50% of them or 90% of them? Okay, so a high recall rate means that we missed very few of the patients we were trying to predict as staying long. But you can imagine there's kind of a gap in there, right? You could do really well at getting everybody that stays long correct by just assuming everyone will stay long. That way you're going to catch them all. And so precision matters. So this precision is going to be how often were we right that someone would stay long for all the patients that we predicted versus how many actually were. So this is bringing into scope, how often were we incorrect in our call that people would be staying long? So these two together really help in thinking about this trade-off with each other. And so if we set a really low threshold, you can imagine we'll classify most everyone as long stay. Let's say if the probability is 2% or greater, we'll call them a long stay. We're going to just say everyone's a long stay. And so your recall is going to be really high to where we are just doing this great job at catching those long stays. But our precision is going to be really low, where we got a bunch of false alarms, okay? So we don't want a bunch of false alarms. That costs us a lot of things in healthcare, actually. So we'll talk about that more directly a little bit later. So in the next cell, we compute that confusion matrix for what this looks like in our data set, and this is the answer. It's helpful, right? It's one way to start thinking about it, but we want to go further. We want to talk about this trade-off and figure out how does this look different across those different thresholds. And so here we've got this really nice visual we put together of trading off between precision and recall. And so you see across that bottom axis, if we change the probability and we only make a call for this will be a long stay patient, if the probability is greater than 20% or 40 or 60 or 80, we'll continue to increase our precision because we will we'll have less errors if we hold ourselves to a higher threshold. But we're also going to start losing people that we make the right call on. And so there's this trade-off. And it's not that we're trying to find the perfect balance between the two. It's that we want to understand this trade-off, and we're going to need to understand it within the context of our problem. So this helps us see that there is a trade-off here between the two along the entire spectrum. And there's a very steep trade-off after about 40-50% probability, which makes a lot of sense, right? Just in the general, problem-solving world. So in summary, that precision tells us of the cases we flagged as positive, how many were actually positive, and recall gives us of all the actual positive cases, how many we caught. So next, we're going to look at those things on a curve, okay, and summarize the trade-offs in a common way that people use here. And so we're going to go ahead and fit those training data sets. We're going to predict and then take a look at how well we did on the testing set and plot those two curves, recall and precision. We saw them against each other, but we're going to look at them on their own because this is a common way people look at to evaluate the accuracy of their models. And so this is what we get. We get with our recall ROC curve an accuracy underneath this curve of 0.903, 90% recall on the test, and a 0.928 on the precision. So in the same range is a really positive thing. And the barrier score has to do with how close our probability was to the actual probability. And so we want this to be as low as possible, this Brier score, sorry. The Brier score being low means that we were within a pretty tight range of the actual probability on each of these cases that we called and predicted. And so we see a ROC curve here that climbs steeply up and to the right into some pretty high accuracy quickly, given those different trade-offs, okay? Those are the trade-offs in probability. Probability of we make that threshold 0.2, 0.4, 0.6, and what kind of accuracy do we get? So as you use a higher threshold, like we'll only call this a true positive when it is over a certain threshold, you catch more people, right? You get 60% of those right, 80% of them. We find close to 100% of them, that 90% range. As we grow up into the right, we seem to sort of top out around a 50% threshold. That's sort of common sense and means that that's probably a range that would make sense as long as we're not giving up too much precision. So let's look at what kind of precision do we give up as we move towards 0.5 for a threshold. And generally what we see on this curve is as we increase the threshold, we will go ahead and start losing precision, reducing our precision here on this. Recall again that come back to some of the stuff I've got for you. Precision tells us of the cases we flagged as positive, how many of them actually were positive. Another useful classification is up here for precision, that of all the patients we predicted would stay long, how many of them actually did. So we start to do worse. Of all the patients we said would stay long, how many of them did stay long? If we have a really high threshold, um, we are still going to get about 60% of those right, because 60% is the proportion that just does stay long in our data set. But we do better across the thresholds here, um, going back towards just calling everybody as not going long, uh, because then you're never wrong at 0. And so in the middle, we see this curve fall at some general rate until we get to about the 70% range. Around 70, that threshold of 0.7 probability, we really drop off a cliff. So notice the really big difference in slope there after 0.7. So for me, that says that I'm comfortable making a threshold up until about this range of 70, because after that we really lose a lot of precision. And since we get the most bang for our buck around 50% trade-off probability of 0.5 here, that's probably the range that's going to be comfortable. But we'll look at how to bring that down to a practical level here later. So we can use this, run this step in modeling in this workflow to help to see how the pipeline is behaving and calibrating this information against the probability based on our predicted probability and what we actually observed. So we want to see this nice tight formation around this 45-degree angle here, where we predicted a probability that ended up being true. Okay, so now I want to talk about our precision and recall versus the threshold before we tune it to see where do we get the best performance. Okay, so we're going to sweep across those probability thresholds from 0 to 1 and compute the precision and recall each one of those. So this helps us see that trade-off. So this is slightly different than the ROC curve. This is seeing just over each other what sort of trade-off we have between this threshold. Instead of just doing those generic curves, I'm bringing out and showing us the probability and where that change happens for each of these before we go down and start doing a bit of a tuning. Okay, so now we want to explore the different values of this the parameters that we can set within our data set, within our approach. So we're doing a logistic regression, and so there's just sort of this one thing that we can use, this regularization strength, to help restrict the data or the modeling, very similar to like our grid search. And so we're going to use cross-validation and plot the results at different levels for this regularization strength. This is very similar to the grid search activity we did before in hypertuning, essentially, is what we're in the middle of here. And just starting to see in a different context of predicting a classifier as opposed to a value, we want to see what happens and how do we understand the trade-off we get for changing this variable and the performance, both on training and of course on that cross-validation. So in blue you see that we get an increased performance by changing that variable only up into a certain point, okay? And so there's steep growth from left to right, and that 10 to the negative 3 over to about 10 to the negative 1 for that value. And then very soon after, it really flatlines. And what's interesting is in the validation data set, we also see an increase in performance, which is good. That means that we do want to adjust this to be closer to that 10 to the negative 1 area. And we get sort of the increased performance in our validated data set, where we actually put it against new data. But after that, we start to actually lose performance. So we don't want to be moving anywhere towards that. So this is where we go ahead and say, all right, we're going to do this logistic regression, and we're going to set the variable that we can adjust for tuning to somewhere in this range here when we go live with it. Okay, so now I want to go and move on to bringing this down to reality, bringing this back out of the numbers, out of the data, out of the graphs, and looking more at, okay, now we need to turn this into something to think about, okay, for our administrative partners. How are we going to decide, is this worthwhile doing? Is this practically useful? So the best way to do that is to think about it in terms of costs. So I'm going to put this fake scenario in front of us that's very realistic, that the reason we're going to predict these long stays is we want to do something about it. We want to go ahead and mobilize a group to go and help these patients. So we collect a bit of information based on our past experience. Number one, we're going to say that it costs about $600 to get this team involved, that this team is going to go and support the patient, but it costs money to send folks and do all of these activities. Okay? Then let's assume that we see a success from this group of about 50%, that they're only able to reduce the length of stay in about 50% of our patients. So an assumption, but we'll try to base it on experience or maybe an expectation. Then we also want to use experience or an expectation, or we can experiment a little bit with it. How much can they reduce their length of stay? So this might be a thought exercise at the beginning of a new POC, or it might be saying, hey, we've got a team, we know their success rate, let's see how much this could help. Okay, so it costs money to send them. They're only useful on, or productive on 50% of the cases, and they can only reduce it by 20%. Okay, so that is all cost, basically. We're wrong on some of these, and it costs money to go do this on every patient. So next, we need some version of, well, what are we going to save, okay? And so I've got this example in here to say each day that patients are in the hospital past that 4th day, our threshold for long length of stay. We've worked with our finance colleagues and learned that costs about $3,000 to the institution. So these are our variables, okay? Cost to mobilize, cost per day when they're in after that long length of stay, the success rate of that team, and the reduction fraction. I'm actually going to change it to 30%. It looks like we can reduce length of stay by 30%. But guess what? We can play with these and work with these to see how it changes our output. What we're going to do now is go ahead and fit and train that data, and we are going to use it. We're going to take this and test it against some actual patients, and we are going to go ahead and predict and use the information and assume that this is what will happen. For everybody we mobilize on, it costs $600. The cost per day for patients here greater than 4 days is $3,000. And so anybody we can help, that 50% they're able to help, and the way they can help is reduce their length of stay by this much. We're going to get back $3,000 for every day that we reduce. So we just do a quick basic modeling of this. If this were to happen, given how right and how wrong we are with our model, here is what we can expect in a net benefit. But guess what? We have to choose in our modeling, what threshold are we going to use? We talked about that precision recall trade-off before, and here's what we actually see. If we use a threshold of 0.5, which we had been discussing, we do get some benefit, okay? Because we save money whenever we get patients out early, but it costs money to do those activities, we get some benefit. You can see the net benefit rising above, $15,000. But guess what? We can get more strict on this so that we are mobilizing less often and we get an even higher benefit. So even though if you were just looking at the numbers, you would look at that precision recall and maybe make a call somewhere in the 0.5 probability range for the threshold, if you were to put this into the real world, you get a totally different picture, that you probably want the threshold as high as 0.6, 0.7 in order to capture the full net benefit possible here, given our situation. So That is the way that you take a predictive task and use the numbers to make sure you're making good decisions about how to set the parameters and how to trade off for this probability threshold, but then bring it back to reality. Let's bring it back and say, okay, here is what it'll cost to make an intervention and the possible benefit, so that we can see how that translates out into our scenario. So to bring that home into a simple, explainable table about some of our options, let's just get this into a table of results to say, if we were to change this threshold, let's say we are very loose, that will, anytime we're a quarter, over 0.25 probability of them being a long stay, we're sending that team, versus 50%, 70%, or 90%. So it's really high conviction cases only. Let's see two things. How many patients are we going to end up acting on? And then was it worth it? Okay. So this is just another way to bring it home to our administrative partners to take that result and say, hey, I was able to produce a predictive outcome and it seems to be pretty accurate. The answer is, so what? The next question, is, so what? So here's your so what. Okay. If we were to use some different thresholds in our choice of how to mobilize this solution, if we get more strict with the threshold of probability when we intervene, our estimate of the probability of being a late stay, here's how it'll change the number of patients we intervene on. We'll move from 163 patients down to as few as 60. So there are really different choices in how many patients we end up helping or addressing, but there's not much of a trade-off between 0.75 and 0.9. If we do that, the 60 that we intervene on, 58 of them we would have been right on. 2 of them we would have said they're going, but they didn't. And so we would have a mobilization cost around $30,000 from that team getting involved with 60 patients. However, because that team has this 50% success rate and can reduce length of stay by 30%, we can have an expected savings of $44,000. And so there's a net benefit there that is achievable. We can increase to a really strict threshold, and we would see a similar result in our performance. So this helps just bring it home to some simple decisions about, okay, how many patients are we willing and able to intervene on? How many of them would we have been right on? And what are the costs associated with that sort of mobilization of the solution? So this is the way that we take this, very mathy point of view of how do we get the data formed and pick an algorithm and hyper tune it and rate and make sure it's not overfit. What does it matter? This is where prediction tasks need to end, and too often aren't getting all the way here with a lot of folks. So this is the prediction task, but brought to a practical level of how do we implement it, what's the implication, and how do we think through those different accuracy trade-offs in order to understand it. I know a lot of really, really smart people who can explain to you everything about the precision and recall and how to evaluate accuracy on a model, and fail to bring their solutions to this level. But I'm fortunate to work with some amazing data scientists who do always bring it back to this practical level. You want to be one of the latter. You can learn precision and recall to the degree you're able to help discuss it and solution with it, but your end result needs to be something simple and explainable about how this predictive task helps us in the real world where we're trying to do something with it. All right, thanks for staying with me on this second version of a prediction pipeline in Python.